Welcome to the video. Kimi K3 has around 2.8 trillion parameters. That sounds almost absurdly large. But here is the interesting part. For any given token, only about 104 billion of those parameters are switched on, that is under 4% of the model. So how can a model hold almost 3 trillion parameters without using all of them for every word it writes? That is where K3's architecture gets really interesting. And don't worry if the vocabulary is new, we'll define every one of these on screen as we reach it. A parameter is a learned number. A token is a chunk of text. An expert is one small specialist subnetwork. A router picks which experts to use. Attention decides what matters right now. And a KV cache holds notes about earlier tokens. We'll build all of it from the ground up. So before we see any of K3's ideas, let's start with that first word, parameter. An AI model is essentially a huge mathematical network, dots that hold numbers, and connections between them. Sitting on those connections are learned numbers, and those are the parameters. During training, the model adjusts these numbers over and over so it gets better at recognizing patterns in language, code, images, and reasoning. More parameters gives a model more capacity. But bigger does not automatically mean smarter. Architecture, data, and training technique matter just as much. K3 is interesting because of how it organizes that capacity. Before we go further, one more word you will hear constantly, token. AI models don't necessarily read text one complete word at a time. They break it into smaller chunks called tokens. A token might be a whole word, part of a word, or a piece of punctuation. The model reads those tokens and then repeatedly predicts one thing. What token should come next? And it does that incredibly quickly. Now we can understand K3's first major architectural idea. Kimi K3 uses something called a mixture of experts, or MOE. Imagine a huge organization with hundreds of specialist teams. When a problem arrives, you don't need everyone working on it. You pick the small group that looks most useful. K3 follows the same idea. It contains 896 routed experts, and every square you see here is one small specialist subnetwork. But for a single token, the model switches on only 16 of them, alongside shared experts that are always on. Which means 880 of those routed experts sit completely idle for that token. One important clarification. When we say expert, don't picture an official Python expert or a maths expert. These are simply specialized neural network components, and their specialization emerges during training. Nobody assigns it. So who decides which experts should process a token? A component called the router. Think of the router as a traffic controller. For each token, it scores all 896 experts and works out which ones look most appropriate right now. Then it sends that token through just the top 16. K3 goes one step further, and this is where the word latent comes in. Every token starts at the model's full width, 7,168 numbers. The two shared experts always see it at that full size. But before the token reaches the routed experts, it gets squeezed down to half that width, 3,584 numbers. That compressed copy is the latent. The 16 chosen experts do all their work down there. That matters more than it sounds, because with 896 experts spread across dozens of GPUs, the real cost is not the arithmetic. It's moving data between chips. Halving the width halves that traffic. Then the result is projected back up to full width and added in. That is stable latent MOE. There is one more problem hiding in that pool of 896. If you let the router pick freely, it develops favorites. A few experts get swamped while others are barely used, and the neglected ones never train properly. So K3 nudges the router with a small bias for each expert. Quantile balancing sets that bias straight from the spread of the scores, so every expert lands on its fair share. It's the difference between grading on a curve and grading on raw scores. So instead of activating nearly 2.8 trillion parameters for everything, K3 activates roughly 104 billion parameters per token, under 4% of the model for every word it generates. And that's the first big idea. K3 can hold enormous total capacity without switching the entire model on at once. And here's something easy to get wrong. You might picture the router sitting at the very end of the model choosing experts once. That isn't how it works. K3's mixture of experts processing happens inside the model's repeated layers. Information moves into a layer, attention processes it, the MOE routes it through the selected experts, and that updated representation moves into the next layer. And this repeats over and over throughout the network. Which raises the obvious question, what's a layer? Think of the model as a sequence of transformation stages. Layer 1 takes the input and changes its representation. Layer 2 processes that new representation. Then Layer 3, and so on. Kimi K3 contains 93 of these layers. Information becomes progressively richer as it moves deeper. And inside those layers, one of the most important operations is attention. Attention helps the model work out which pieces of information matter right now. Imagine reading this. Sarah put the laptop inside the backpack because it was safer there. When the model processes the word it, that word on its own means almost nothing. So, attention looks back at earlier words and builds relationships with them. Laptop, backpack, it weighs which of them the word it actually depends on. So the model is constantly asking, what should I look at before deciding what comes next? Transformers became extremely powerful because of this, but it creates a challenge. Because before we can see what K3 changes, we need to understand what breaks. With 10 tokens, every token can compare itself against every other token. That's about 100 comparisons. Easy. But that cost grows with the square of the length. Double the context and the work roughly quadruples. Across hundreds of thousands of tokens, computation and memory explode. And Kimi K3 supports a context of 1 million tokens, so it needs a far more efficient way to move information across very long sequences. Enter Kimi Delta Attention. Kimi Delta Attention, or KDA, is a form of linear attention. You don't need the equations to understand the purpose. Traditional full attention compares lots of tokens directly against lots of other tokens, every pair, every time. KDA instead keeps a compact recurrent state and updates that state as each new token arrives. Information travels forward through the state rather than through every pair. And that is where the word delta comes from. Rather than overwriting its state with each new token, KDA works out the difference between what it already believed and what the new token says, then applies only that correction. A channel-wise gate lets each part of the state fade at its own rate instead of everything decaying together. Think about reading a long book. You don't hold every sentence from every previous page in your mind. Your understanding just keeps getting updated. This character is important. That event changes what happened earlier. This fact needs remembering. The mathematics is very different, of course, but the idea is the same. Maintain and update useful information efficiently as the sequence grows. That's why it helps with long context. This also connects to another phrase you've probably heard, the KV cache. When a transformer generates one token after another, it doesn't want to recompute the whole past every single time, so it stores intermediate information about earlier tokens, and that store is the key value cache. Think of it like keeping working notes beside you while you read. Very useful, but the pile grows with every token, and once the context gets extremely long, those notes consume a lot of memory. Architectures like KDA reduce the dependence on that token-by-token growth, because a running state doesn't have to expand the way a full attention cache does. Which brings us to the other half of that name. What is MLA? MLA stands for multi-head latent attention. In ordinary attention, every token stores a full set of keys and values, and that is what fills the cache up. MLA squeezes all of that into one small latent vector and stores only that. The keys and values get rebuilt from that compact vector while attention runs. Same full global attention, a far smaller cache. But Kimi K3 does something clever here. It doesn't use KDA everywhere. Across its 93 layers, 69 are KDA layers. The other 24 are gated MLA layers, and they're interleaved on a regular pattern. 3 KDA layers, then 1 gated MLA layer over and over. You don't need to memorize the term gated MLA, just remember the architectural role. KDA gives the model an efficient way to carry information over long sequences. Then, periodically, gated MLA restores a form of global token-to-token attention, so tokens can interact directly across the whole context. K3 combines both instead of choosing only one. Now we get to another very interesting K3 idea: attention residuals. But before the mechanism, one piece of vocabulary. What is a residual connection? In deep neural networks, information from earlier stages is carried forward, so later layers don't lose useful representations. Traditional residual connections keep accumulating everything into one running stream as you go up the network. K3 introduces something more selective. Attention residuals let a layer reach back across all preceding layers and attend to whichever representations are useful right now. Imagine solving a difficult problem. You're now on step 20 and suddenly something you discovered at step 5 becomes important. Instead of treating every previous step equally, you want to retrieve the earlier one that actually helps. That's the intuition behind attention residuals. Here's the easiest way to remember these two ideas. KDA improves information flow across length, across lots of tokens, left to right. Attention residuals improve information flow across depth, across lots of layers, top to bottom. KDA across tokens. Attention residuals across layers. If you remember that, you've understood one of the most important ideas in K3. Kimi K3 isn't built only for text. It is multimodal, and multimodal simply means an AI system can work with more than one type of information. Text, images, and video frames can all go in. The visual ones first pass through a vision encoder called MoonVit v2 with around 401 million parameters. So what does a vision encoder do? It converts pixels from an image or from video frames into mathematical representations the rest of the model can already reason about. Pixels come in, MoonVit converts them, and K3 reasons about what it sees right alongside language. This becomes especially powerful when K3 is used inside an AI agent. Imagine asking an agent to build a website. The model writes the code. The agent runs it and captures the screen. K3 inspects the result, sees the layout is wrong, and edits the code. Then it runs it again and looks again. Together, that forms a loop: perceive, reason, act, and observe again. One important distinction: the model itself isn't opening browsers or executing programs. An agent framework gives it access to those tools, and that combination is increasingly how real-world AI systems get built. Now let's put everything together. Your input enters the model, text or images. Text becomes tokens. Images are processed by the vision encoder first and come out as representations the model can use. Then information starts moving through K3's 93 layers. Inside a layer, attention determines what information matters. Most of those layers use KDA, efficiently carrying information across long sequences. Every fourth one uses gated MLA for more direct global attention. Attention residuals let the layer selectively retrieve useful representations from earlier depths. Then the mixture of experts block. The rotor scores all 896 rooted experts and sends the token through only 16 of them, alongside the shared experts. That transformed information moves into the next layer, and the whole process repeats 93 times over. Eventually, the model predicts the next token, then the next, then the next. So tomorrow, if somebody asks what's interesting about Kimi K3's architecture, you don't need to remember every technical term. Remember 4 questions. Mixture of experts asks, who should work on this token? Attention asks, what information matters right now? KDA asks, how do we carry information efficiently across enormous sequences? And attention residuals ask, which earlier layer representations are useful right now? So the most interesting thing about Kimi K3 isn't simply, wow, it has 2.8 trillion parameters. The deeper story is how those parameters are organized and how information moves through the model. Use only a small set of experts at a time. Carry information efficiently across huge contexts. Retrieve useful representations from deep inside the network, and combine language with vision. That's what makes the Kimi K3 architecture worth understanding. Because the future of large models isn't just about making them bigger, it's about making that scale more intelligent, more selective, and more efficient. Thanks for watching.